Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 6.2, Volume of Revolution. So this topic, Volume of Revolution, was used to be in Mechanics 2 paper, and I think it's Mechanics 2 anyway. It might be Mechanics 3. It is essentially summing up the volume of stacking disks, which, according to the definition of integration, works fine. So let's take a look at how to do that. Okay, so for examples, let's try to find the volume of a sphere. So as we know, a sphere is essentially a circle on a 2D plane rotated. So let's have a circle that looks terrible, but it is a circle indeed. We have, let's take the unit sphere where x is 1 and y is 1 for maximum and minimum. Well, minimum is -1 and -1 respectively. So with that said, what we can do is to look at the whole thing, and turns out that if we split it into strips, we have essentially lines of radius of certain disks. If you have the radius in disks, so you will end up having something that looks sort of like this, stacking together, and that would, although that looks pretty terrible, that would look like a sphere when you stack them together. So this is what we're trying to do. So first of all, we want to find the radius of the circle, such that when we rotate by 360 degrees, we can get a volume. So what we need to do is to find the radial component. I'll put it as r for now. Integrate it from -1 to 1 across the x direction, so dx. So this is our expression that we want to use, but with that we only have the r component, so we are just summing up the lines. What we actually want to do is take the r, turn that into a circle disk area expression, which we know is pi r squared. And essentially, if we take that in, actually r is a terrible idea, a is a better idea, so area unit, then we have pi r squared, and turns out that the value of r is also the same as the y coordinate, so we can turn that into pi y squared. So what we have eventually is the integral of pi y squared dx. This is a general form of integral for volume of revolution, which you have a component which is a radial component of whichever axis you're rotating across. Then you have the axis of rotation, so basically these two variables will be opposite of each other. So if you are rotating around the y-axis, so you're going this way, then you will have a pi x squared dy expression for this particular revolution example. But since we're rotating around this way, clockwise or anti-clockwise, doesn't matter by the way. We are using this expression, and always state your limits that are valid. And finally, we want to actually evaluate this whole thing. We cannot evaluate this because we have a y squared here. Luckily, we can, by using just Pythagoras, or if you like, you can use the the radial, the polar coordinates, there we go, to find what x and y are. So x squared plus y squared is always 1, because we have a unit circle, so this holds true at all cases, so we can tell that y squared is 1 take x squared. Convenient. Just plug that in with y squared, we get pi integral 1 minus 1 take x squared dx, which is pi x take x cubed on 3, 1 minus 1, which gives us, let's see, so x take 1/3, x is 1 take 1/3 is 2/3, then take away a negative 2/3, and guess what? We have 4/3 pi, and according to the limits, we have a unit sphere, which is supposed to be 4/3 pi r cubed. So 4/3 pi r is 1, so r cubed is also 1, so we have the correct volume. Yeah, this example is relatively straightforward. You can extend this to any curve, any function that is continuous. You can do volume of revolution with. I think something you need to take care of in particular is when you have a curve that goes through the x-axis and you need to rotate through. Best bet, do it in 2 parts. Sometimes it doesn't matter, sometimes it does. I'd rather not take the chance that it might matter, so I'll cut it into domains, then integrate. Yeah, basically what kind of question you'll have is you'll be asked to find the volume of revolution given a certain function, fx, and yeah, basically rotating through x-axis or y-axis. You wouldn't be asked anything in between, so that should be fine. So volume of revolution is highly likely to occur in section B of the paper, because normally it would be a long question. Probably there will be case study kind of questions that you are asked. So a farmer was building a farmhouse or something that is cylindrical, and you need to find the actual storage volume of the entire hut. Something like that might come up, and you will be asked, not directly, you will have to imply that they're asking you volume of revolution in that sense, or maybe the volume of the vase or something. Let's see. Yeah, there aren't much else when it comes to volume of revolution. It's quite straightforward, so if you can do them, easy marks for you to take home. With that said, now it's time to do some practice, because without practice, nothing is easy. So questions are set. 2 questions today. Find the volume of revolution of the following. So I've specified the axis of rotation and the domain of rotation, and the expressions are shown below, and you can just do the integration and find the volume. So yeah, essentially I'll just wait you for 5 seconds to pause and do the questions, and I'll show you the answer in 5, 4, 3, 2. So here are the answers. I might have set these questions a bit too easy, but anyway, you can always find more practice online, or if you ask your school teacher, you will find some more. But yeah, basically that's it for this video. I hope you've learned something. If you have any questions to do with volume of revolution, do let me know in the comment section below. And for now, thanks for watching, and I will see you on my next one.